Okay, and with that, it's time for the final talk of this year's PriSC, as someone we have already seen today. So I guess I don't have to introduce you again. So let me immediately give you the floor.
Thank you. This is the title with, or the sorry, this is the talk with a longer title, towards a modular specification and verification of a concurrent hypervisor-based isolation. So it's a little bit odd as the second talk, but I talked about our virtualization platform. And this is what it looks like kind of at the implementation level. I mentioned it was this microkernel. And so that's this Nova piece. Nova is this microkernel. And on top of the microkernel, we run a variety of applications, a virtual switch, the VMM application that we talked a lot about in the last talk, this UMX, the console multiplexer, and this master controller. And there's this interesting thing up here with this customer services that could be people running other processes which have not been verified on top of this microkernel. And our big ambitious goal, as I mentioned in the last talk, is to verify this stack against a strong user space specification. And that specification might be something like runs these virtual machines correctly or something like that. The focus of this talk, unlike the last talk, this talk is going to be about Nova. And in particular, how do we draw this, like what is the formal representation of this black dashed line? And how do we prove things on top of it? So to set that up, I have to tell you a little bit about what Nova is. So Nova is this microkernel. And it exposes 15 or 16 hypercalls. I believe there's 16 possible, and one is reserved for future use. It basically divides the system up into a bunch of different resources. This is kind of what it looks like at the hardware implementation level. The blue components here are reflected into user space, okay? So one thing that's different from commodity operating systems is that devices, all device drivers are written in user space. And we'll have to find a way to reason about user space applications that are driving devices. Memory is obviously accessible, but things like page tables, this memory controller and SMMU, for example, are privileged and therefore controlled exclusively by Nova. So the API has 5 kernel objects. This is a capability-based microkernel. It's got protection domains, which mean basically address spaces, which include both memory and objects, pointers to other objects. It's got threads, which are made up of ECs and SCs, portals, which are a means of doing inter-process communication, and semaphores. And for the purpose of this talk, the most understandable of these things is semaphores, so I will talk about that one. But before we go into that, let's talk a little bit about where we're going to go in this talk. So I told you a little bit about the implementation. It's written in C++ in assembly. That adds its own level of complexity. But I'm mostly going to focus about the specification and how we express that in separation logic. Then I'm going to talk about 3 different things we're aiming to prove on top of that specification. One is going to be verification of user space applications, so we know that the whole system does something useful. Generally, the interesting thing about operating systems don't do anything useful to people outside of the computer, and that's kind of nice. So we're thinking about, running a web server on Nova means your computer will act like a web server. We're going to think about robust safety, showing that Nova is protected from user space applications, no matter what user space applications you run. And we're also going to think about those situations I mentioned before, which is where some of your applications are trusted and some of them are not, and establishing robust safety of trusted applications or verified applications against unverified applications, and see how we can do some of those proofs on top of this and speculate on how we can do more of them. All right, so this is what the Nova specification looks like. It is not 12,000 pages, thankfully. It's only about 100 pages or so, I think. This is control SM, which is the thing that does semaphore up and down. And the way we express this in separation logic is we build so we say there's 2 pieces of ghost state attached to every semaphore. Every semaphore has a value, and it has a list of waiting threads. Okay, and so we express those in separation logic by this SM value. G here is going to be the name of the semaphore. So SM value G0 says the value of the semaphore named G is 0. And SMQ GLS means that LS, the empty list says no one's waiting for the semaphore. And then to specify what does control SM do, like for up or down, this is what it says. So this is written in predicate transformer style. We say the weakest precondition of the hypercall of control SM with doing an up is first take the number, because we can't have pointers in this model, because pointers into the kernel would obviously be very bad. So instead what we do is we take a number that's local to our protection domain, and we resolve that to an object. Now that object might have the correct or adequate permissions, or it might not. If it doesn't have adequate permissions, we'll just stop. We'll immediately return bad cap, I think is what the error is called. But if we do succeed, then we'll use sminker to atomically, using an iris atomic update, to atomically increment the value of sm.value. So it'll go from v to v+1. For the purpose of presentation, I'm ignoring the potential overflow there. So the idea here, the takeaway message from this is that when you want to specify a hypercall like this, or when you want to specify functions like this, they're generally commit in multiple steps. So we can't just do it like a hypercall commits in many steps, potentially very many. And you also need features like non-deterministic choice and things like that. And all of those ideas are easily expressed using separation logic assertions, so we can give nice predicate transformer semantics to them. I should say that a lot of things I talk about are just the specs. This spec is actually proven. We've actually verified C++ code inside of Nova that does all of this. It proves this specification of the control SM. It calls functions that are only specified for things like scheduling, but all of the logic around SM up and SM down is all verified within Nova right now. All right, so we need to take that WP hypercall and kind of plug it into and use it to describe the semantics of user space. And we do that via this axiom, or via this definition, WP Nova EC. That's going to be the weakest precondition of a thread running in Nova in user space. And we can think of it as that thread has some register state, and Peter and I had a long discussion in the break about what is the register state of Nova, of an application running on top of Nova. But for most of you, you could just think of it as registers. And that thing's going to take a step, possibly emitting an event. That event might be a hypercall. I need to do a hypercall. And so then we'll just dispatch this WP hypercall. And then when that hypercall returns, we'll end up going back and resuming the execution of that user space thread with updated register states. All right. And this is posed as the axiom that we give in Nova that tells you how all these things work, but this WP Nova EC actually is given a definition inside of Nova. And the theorem that we prove at the beginning of Nova when you start up is something that looks like this. It says you give Nova all the resources of the machine, so all the memory resources, all the device resources, all that. It consumes all of those down here. You also give it kind of ownership of the execution of the CPU. And you also tell it you can kind of behave like this. Right, so this is what user space is going to do. There's that WP Nova EC. So what's above right here, this is all the resources that are given back to the user. So Nova's wrapping them up, re-exposing the raw resources as Nova resources. All right, so that's the specification that we're going to give to Nova. We aim to prove that using a variety of great proof techniques and axioms about C++ and whatnot. So now let's talk a little bit about how we might take that proof and build interesting verifications on top of it. So if we imagine that when we boot up, when you push the power button on your machine, you might start like this. There's your CPU running over here, and you have to behave like that. And you've got all your physical state. You're probably the only one running at that point, though in reality, there's so many things that run before you, it's ridiculous. And you want to act like the spec init thing. And we think about this using a technique from a very long time ago called carousel, which basically says that if you prove something like this, set up in an appropriate sort of way, you can use iris adequacy, iris didn't exist at the time, to extract a proof of operational refinement between these two things, as long as you make sure that spec init is adequately connected to the operational semantics of the underlying machine. And then using this theorem, so that's what we want to prove, and if we can prove that, we'll be able to get this nice refinement property. We can apply that theorem Nova OK that I just said, and that won't mess with the left-hand side of this entailment because we have framing and separation logic. But we'll use that and we'll forget about the raw resources and we'll end up with the Nova resources, okay? And then I can take that and using some assumptions about C++, I can review the fact that I've loaded a program that just happens to be the compilation of a C++ program in memory. And I can kind of think about that as being like, well, let's think about those bytes instead of being actual bytes as being some program in memory. And then I can prove spec in it entails that C++ program. So that basically says, if I prove my program correct against this carousel style specification, I'll be able to compose that with the C++ axiom and the Nova proof and ultimately extract out this adequacy theorem. So that's the way that we aim to verify interesting properties of this whole system that's built by this stack. All right, so now let's talk a little bit about robust safety. So you recall that in the Nova specification, we had to quantify over all startup images, okay? So that seems like it's pretty good, but we also gave you this kind of weird thing, and it's not entirely obvious that this is provable. Like maybe WP Nova EC is just false, and it's very easy then to prove this theorem. And Nova just becomes unusable. But if we can show that this assumption is provable for any startup image, whether it's good or bad, then we'll basically be showing that Nova is usable. And the way we aim to do that is by constructing, well, we need to prove this, that those user space, so we're gonna construct an iris invariant here. We're gonna need to show that those user space invariants are sufficient to build that iris invariant, RSINV here. And we'll show that RSINV is sufficient to prove that WP Nova EC appropriately. And you can see basically what we're doing here. We are taking all the state we own and we're existentially quantifying over the V's and the lists of execution contexts. So we are not going to be able to say anything using this invariant. We're not going to be able to say anything about the value of the semaphore, but we're going to be able to say there is a semaphore. And because of the setup of our specifications, the fact that there is a semaphore is enough to justify that I can take a step. So it'll be enough to prove this theorem, and mainly this bottom one that says that WP Nova EC is provable using just RSINV. All right, so now on to the last of these, which is kind of interesting, where we have hybrid clients and we have verified and unverified code working together. So here's the example. Nova is kind of like a very low-level thing, and a lot of people want to program in something that's not quite as low-level. In the Bedrock stack, we have a master controller that runs on top of Nova, and then user space applications talk to that. And what we see is that the master controller is usually the one that's communicating with Nova, like saying, create me a semaphore. And when the master controller asks for a semaphore, it's going to get exact ownership of that. It's going to know the value of that semaphore is currently 0, and there's no one waiting on it. And that's important so that he can put his own policy on it. Maybe he's going to use it as a synchronization primitive or something like that. But he also wants to be able to give that semaphore potentially to unverified code. And then he has to carve up some protocol that describes that will be robust against this guy. So he knows that no matter what this guy does, he can't violate that protocol. All right, I'm just about done. And that can be achieved in separation logic by carving out a slightly smarter invariant. So for example, if the master controller wants to give shared ownership of a semaphore to this unverified code, but say he only gives up permissions. He says, you can up the semaphore, but you can't down it. Then he can easily carve out an iris invariant for just that semaphore that maybe has a lower bound. So he says, I don't know how many times this guy might up it. Maybe he'll never up it. Maybe he'll up it a lot. But I know that if I don't down it, the value will be at least 3, for example. I don't know what that thing might be. So he'll be able to make assertions about portions of the state in interesting sorts of ways. And we've done some experiments about how we can both give state out and also revoke it. Revoking is much more difficult because you kind of have to show that his capability space, he couldn't have tucked that semaphore anywhere that you didn't know about. And the way that's handled in our setup is the master controller can track everywhere where this guy puts that capability. So he can go in, and the master controller can remove all of those ways that he has to access that. And after he removes the last one, he can kind of show, okay, there's nothing that guy could have done, so I can kind of take that state out of the invariant and have a hold on it sequentially now. All right, so that's it. Right, so I told you a little bit about what Nova is, how it works, but mainly how it's specified. We've got this WP of user space threads in Nova. Then I told you how we have done many system verifications on top of that. We, for example, verified a user space synchronization library with semaphores and reader-writer locks and things like that on top of the Nova specification. So that's verified in C++. The C++ library that runs in user space is verified on top of the Nova specification. Told you how we aim to prove robust safety. That's not a completed proof, but we've done some sketches of it, and we believe that is very tractable. And we have done some additional actual proofs of hybrid clients, kind of establishing some of these smaller invariants. But we have not done a revocation proof at this point, and we think that would actually be very interesting, but we'll have to wait for the next time. So that's all I have. Thank you very much.
Questions?
John?
I am kind of curious about the claim that robust safety is tractable. I mean, because you need to kind of inspect all instructions of the machine and make sure that none of them does something that allows privilege escalation. So how do you manage to do that for a large architecture?
That's a good question. That's an excellent question, actually. And that it builds off the contents of the last talk. So the idea is that one of the bits of unprivileged state is going to be basically the register file of each thread. So that's completely unknown. But we know that machines don't actually get stuck, or we assume machines don't actually get stuck. So there's always a transition that can be taken from any register state, and it will emit one such event. And the number of events that we have is relatively small. Does that make sense? So basically we're saying it doesn't matter at all if the user space application is incrementing this register or whatnot. All we have to think about is when it starts interacting with the outside world, or sorry, not the outside world, with coming out of the CPU, out of the unprivileged piece. So that's going to be making a system call, accessing memory, taking a fault. All of those things involve the rest of the machine, and we'll have to prove that all of those preserve that invariant. And basically, it would be thinking about this. It would be the interesting part will be case analysis on the event. So we know one of those events will happen. And we have to show that all of the branches of that match preserve that invariant. Does that make sense? Okay.
I guess a timer interrupt is also one of the events that can happen.
Timer interrupts are actually not exposed to user space. So what happens? So timer interrupts are fully absorbed within Nova, and that's captured by the fact that we could have multiple threads running WP Nova EC, and Nova can pick which one, kind of like cooperative, but not really cooperative threading. But device interrupts are actually also owned by Nova, but Nova accepts the device interrupt, ups a semaphore, and then does not actually pass it on to a thread. So the way that a thread would wait for an interrupt would be to wait on a semaphore. That's how interrupts are exposed to user space.
Other questions? Okay. Can I ask about like you talk about system verifications and you mentioned some libraries. Do you also intend to verify like full systems that involve some user space application where you want to prove some end-to-end property about, I don't know, interaction with peripherals or whatever, and on top, for that application running on top of Nova and
Yeah. So we have verified several applications up there, or we are in the process of verifying some of these applications. So we've verified device drivers that talk to devices and drive, for example, serial ports and stuff like that. The UMX here is a verified application. It's a console multiplexer. So if you type, you could say, I want to talk to VM number 3, and it will properly route your bytes to that VM. It doesn't say anything about what that VM is going to do with it, but it does tell you that that VM will get the stuff. We've also, one of the things we're working on and we're nearing completion on is this vSwitch, which is kind of like that console multiplexer, but it is it acts like a switch. So it's like an Ethernet switch. All of your CPUs or all of your guests are connected to it by VirtIO, and it will do packet exchange. So you can send a packet to Dominic or anyone else.
And since you're using Iris, I expect the kind of adequacy you get is then just like safety properties or what?
Yeah, we're just focused on safety properties. Right?
Not confidentiality, not liveness.
Not confidentiality and not liveness, yes. Liveness we aren't too worried about. Confidentiality I think people would be very interested in, but I think, at least I'm not aware, maybe other people in the community are, good ways to actually say that, especially in the presence of things like timing channels and a lot of non-determinism that exists inside of Nova. That's can be difficult to reason about.
Can always over-approximate confidentiality as a safety property through taint tracking, right? So if you're fine with an over-approximation of confidentiality, I should be good.
We will get a notion of isolation.
Oh, so right. Sorry, there was a notion of confidentiality specifically for robust safety in the paper from like 2007. Does anybody remember the name? So like, with respect to like confidentiality with respect to something like a fresh value. I forgot the name.
I'm not sure. Sorry. Oh, I was saying we are interested in isolation properties, and we the same sort of thing I mentioned about revocation is this sort of thing you would see for an isolation property.
Maybe a last question by Amin?
Yes. Maybe a stupid question. You said that you're doing refinement, but it was not clear to me what is the other side of refinement? What are you refining?
The specification?
Yeah.
Is that what you're asking? So in this case, it's probably better in the previous talk. So yeah, in the standard use of like download the Nova, but download the Bedrock stack and run this, spec in it would be the specification of what it means to run your guest code. Mm-hmm. So it's like you would say, I want to run this Linux live CD or something like that on the Bedrock stack.
Right.
The specification you would get is that we behave in a way that you could also see if you just put that CD into your, people don't really use CDs anymore, but the USB stick into your computer and booted Linux off of that, where there's no hypervisor, right? So we're basically proving that the Bedrock stack doesn't exist in that case. Like it's as if it doesn't exist. We're not adding any new bad behaviors to the system.
Right.
But then we have other features in the stack that you can enable that would allow you to introspect and do antivirus or things like that inside, from the outside, but applying to the guest. So protect the guest from kernel corruptions or something like that.
So does it make sense that you quantify over all guests basically, or what in your theorem?
Yeah. You would quantify over all guests.
Yeah. Okay. Mm-hmm. All right. Thanks.
Yeah.
Okay, so I think I should pass the floor to Shweta now.